Okay, so Physics 11, we are now starting our next unit. This unit is called dynamics. It's a huge aspect of physics. So the stuff that you're going to learn in this little section, actually a relatively large section, is going to be huge as you continue any other sort of work in physics. So when we talk about dynamics, we're really going to be talking about forces and different forces that kind of have an effect on different objects. So today we're just going to look at something real quick, something you may have already talked about before in other science classes, but just kind of the difference between mass and weight and how we can use the force of gravity to help calculate your weight depending on where you are. So that's what we're going to start with today. All right, so like I said, with dynamics, we'll be talking a lot about forces. So this whole unit does talk about the different forces that can act on an object. So I'm going to just talk about a couple here in this class. So again, you should be starting another vocab journal. Okay, so this would be like your vocab journal for Unit 3 here on dynamics. So anything that's bold and underlined in the notes, again, that would be vocab. Okay, so when we talk about inertia, okay, inertia is the property of matter by which it continues in its existing state of rest or motion in a straight line unless that state is changed by an external force. And this comes down to a big physics observation and realization back when it was discovered about how an object, if there's no other forces acting on it, will continue on its same path, right? So a couple examples here. If you're thinking about being in a car and then all of a sudden the car makes a sharp turn, you feel your body moving with that, right? It's moving to the side. And what's happening there is that your body was moving in one direction with the car, and then as the car made a turn, your body still kind of wanted to move in that same direction, which is why you kind of feel that pull, right? Because your body's still wanting to move in one direction, but it's being acted upon by that turning force of the car, which, you know, it causes you to kind of move to the side, okay? Another example would be like a ball rolling down a hill, right? It's going to just keep rolling and rolling and rolling and rolling unless some other force stops it, whether that's a person applying a force to stop it or whether the friction that exists between the ball and the grass or the concrete eventually slows the ball down as well, right? Or even if it starts, you know, it hits a point where gravity starts taking a hold of it, right? If it's it's finished going down a hill and then it starts trying to go up another hill, eventually gravity affects it, right? Another example again is a football player's tackled and his head hits the ground, right? The impact of hitting the ground is going to stop his head, but the brain that's inside of your skull is going to keep moving until it hits that, again, external force of the skull itself, right? So this is kind of where your concussions are coming from, okay? So again, like I said, this lesson is going to focus on, again, the big difference between weight and mass. So again, two important things to define here in terms of vocab, right? When we talk about the mass of something, you're actually talking about how much matter, essentially, is there in an object, okay? How much of something there is. And that's not going to change at any time, right? No matter where you are in the world or in the universe, your mass is the same, right? If it's, an object that has this particular mass, okay, it's how much of it there is. And if we're assuming that that's constant, it doesn't matter where on Earth or where in the universe that is, it stays the same, okay? Weight, on the other hand, when we talk about weight, we're talking about the force of gravity acting on a particular mass. So an object's weight is going to change depending on where that object is located, right? So depending on maybe different altitudes or in different mediums, right? Your weight may change because there's other either the force of gravity is less, or there's other forces acting on whatever the mass is. Maybe it's your mass or somebody else's, or some object's mass, okay? But weight will change. Now, the biggest thing that we talk about when it comes to weight comparisons is on different planets, right? Because we know that different planets are different, like the moon, it has a different force of gravity, right? Because the mass of the planet, or the moon in this case, is a lot smaller, so therefore it doesn't have the same pull right towards the center. So that would mean that it doesn't, you feel less weight because there's less of a force pulling down on you onto that surface of the planet. Okay, so yeah, I kind of already talked about this, right? So if we see that the weight changes as location changes, right, you feel like you actually do weigh less on the moon. Your mass is the same, right? But you weigh less because the force of gravity on the moon is approximately 1/6 of that on the Earth. Okay, your mass is the same. on the moon or Saturn or any other possible planet, but your weight does change, okay? So in order to determine weight, what we do is we multiply an object's mass multiplied by the force of gravity on whichever object, planet, location it's on. Okay, so you see here this equation of Fg, right, the force of gravity, which is essentially your weight, is equal to your mass multiplied by the force of gravity. Okay, so again, key things here in terms of units. Okay, mass must always be measured in kilograms. So if something's given to you in grams, you're going to have to convert it to kilograms. Okay, G is our acceleration due to gravity. All right, so on Earth, that's our 9.81 meters per second squared, right? So you'll see this as an acceleration with units of meters per second squared. And what you get when you multiply those two together, right, is kilograms times meters per second squared, but that's actually been defined as a Newton, okay? So what a Newton is defined as is how much force it takes to take a kilogram of mass and accelerate it by 1 meter per second squared. Okay, that's the formal definition of a Newton, but in terms of units, we can typically just call something with a capital N. We say this many newtons of force, knowing that since newtons are calculated by taking a mass and multiplying it by an acceleration due to gravity, right, you end up getting this kilogram meters per second squared. Okay, so that's called a Newton. So obviously you will need different gravity values depending on where you are, either on the planet or on in the universe itself, right? So you'll start seeing these things here about how, like, your acceleration of gravity when you're at the North Pole is actually stronger, right, than it is at the equator, okay? Versus it's less again at Mount Everest, right? You're further away from that center, like above the Earth, so it pulls on you a little bit less, right? But if you are down at the bottom of the Marianas Trench, again, you're closer to that center, so you're feeling a higher force being pulled down, right? And then again, you'll notice different forces of gravity based on places in the universe. So here, International Space Station, 9.0798, so you're floating a bit more there, right? On the moon, acceleration due to gravity is 1.64, Mars 3.72, and Jupiter, because it's such a larger mass, that acceleration due to gravity would be 25.9 meters per second squared, right? So again, all of these units are in meters per second squared. So again, if you're going to talk about feeling, you're going to feel a lot lighter on the moon versus you're going to feel a lot heavier on Jupiter. Okay, so this is a chart that you'll want to refer to for some of the practice questions or assignment questions that might come up. Okay, so just remember that this is here. If you want to copy it into something, you can. If you want to just print off this one slide, you can do that too. But anytime I ask you for questions and it's using acceleration due to gravity at different locations, use this chart to get the value. Okay, so we'll just do a couple sample problems now. Relatively straightforward ones. Okay, so in this first one, you are going to calculate the weight of a 4 kilogram mass on the surface of the moon. Okay, so if we do that, right, anytime we're solving physics problems, we start by listing our knowns. So what we know is that the mass is 4.00 kilograms. Okay, we're talking about the surface of the moon, so our acceleration due to gravity here is going to be the 1.64 meters per second squared. That was from that table on that previous slide. And forces of gravity act in a downward direction, so I'm going to indicate that with down, because force is also a vector, so it does need to have direction. Okay, so with force of gravity, it is pulling it down. Okay, so we have our mass, we have our gravity. What we're being asked for is the object's weight, right? So we did that calculation, right? So write the formula out. The weight is calculated by taking the force of gravity is equal to the mass times the acceleration due to gravity. What we're being asked for is just that, so we don't need to rearrange the equation at all here. So now we can just start inputting our values. Mass, 4.00 kilograms, multiplied by our acceleration due to gravity, 1.64 meters per second squared in a downward direction. Okay, we just multiply these two values together, and we get a value of 6.56. And again, the units here are kilograms times meters per second squared, which are defined as newtons. And again, because that didn't have a direction, but that's multiplied by down, right? So the object's weight is 6.56 newtons down on the surface of the moon, right? And you can always kind of write that out, right? So the object's weight is 6.56 newtons down on the surface of the moon. Okay, so there's our first example. All right, if we go back to our slides. Okay, so again, you see that same thing there, right? So like finding the force of gravity, looking it up, writing out the formula, putting in those variables, doing the calculation, and then, like I said, the weight of that object is the 6.56 newtons down. All right, let's do another practice problem here, this time manipulating the formula. So in this case, assume a student is standing on a scientific spring scale on Earth and finds that he weighs 825 newtons. Okay, so spring scales are measuring devices that measure the force of an object in newtons. It doesn't actually measure a mass in this case. So this person stepped on a scientific spring scale and has gotten a weight in newtons, and our job is to now find his mass. Okay, so again, let's go solve that. So again, things that we know, right? So we know that its weight, the student's weight, which would have been the force of gravity, is 825 newtons. And that would again be down, because gravity is pulling down on the student. Okay. We know that it's on Earth, so we know that the acceleration due to gravity, g, is 9.81 meters per second squared, again, pulling down towards the surface of the Earth. And we are being asked for what is the mass of that particular object, right? Or this person per se, right? So again, the formula we're using here is weight, or Fg, is equal to mass times acceleration due to gravity. We're being asked to solve for m. So to rearrange this formula, we would just divide both sides by g. So it's Fg divided by g is equal to m. So we take our 825 newtons going down, and we divide it by our 9.81 meters per second going down. Meters per second squared. And when we do that division, right, the downs kind of cancel each other out, right? So it would be kind of like two negatives dividing and giving you a positive. But again, mass is not a vector quantity, it's just a scalar, so it's not going to have direction, it's just going to be a value in kilograms. So when we do 825 and we divide it by 9.81, we get a mass value of 84.1 kilograms. All right, so this object, or this student, has a mass of 84.1 kilograms anywhere, right? Weight of 825 newtons on Earth, mass of 84.1 kilograms anywhere on Earth or anywhere in the universe. Okay. All right, so that's really all I wanted to kind of get you started with. Again, there's the solution typed out, and just try a few of these questions. Okay, so just starting out really nice and slow, nice and easy with just the difference between mass and weight, right? Kind of being introduced to this new unit of a Newton and this idea of a force, right? Force is being measured in newtons, and you can just try these 4 questions from the textbook page that I'll have posted to Google Classroom, solutions there as well, and then we'll get started on another lesson on Newton's laws next. It'll be a little bit longer. Okay, that's it.